Okay, so thanks very much, Anshul, and welcome to the virtual talk.
Thanks so much, Kemp, and thanks so much for that generous introduction. You know, I'm always hesitant to advertise my blog, and so thank you for doing that for me. It's a real privilege to be here today to be able to give this seminar. So thank you so much for the invitation. So as Kemp mentioned, you know, in the last few years, so I just started as a faculty member at UCLA. So I'll be talking a little bit about my some of the postdoctoral work that I performed over the last 3 years or so. And as Kemp mentioned, you know, in these experiments, we looked at sort of out of equilibrium systems, you know, where we would excite a material with light and sort of watch its time evolution, right? And you know, I'm going to be talking about two particular systems today, and both have to do with density waves. And as I go on, I hope to give you an idea of the kinds of things that we can look at in out of equilibrium systems, and you know, why looking there might be interesting. So before I get started, I just wanted to thank a few people who are involved in the scope of this project. In particular, all the work, as I said, I did as a postdoctoral student while I was working with New Getic at MIT, and this work would have not been possible without the, you know, extensive help of, you know, my partner in crime for most of these studies, who is Alfred Zong. He's an outstanding graduate student now, a Miller postdoctoral fellow at Berkeley. So in addition to Alfred's help, we also got some help doing sample preparation from the group of Pablo Herrero. You know, sample preparation for these kinds of experiments is really tough. The samples actually came from Ian Fisher's group at Stanford, and we got theoretical support from Boris Fine at Skoltech and his group, in particular Pavel Dolgarev, who's now a student at Harvard with Eugene Demler, and he's continued to collaborate with us as this project unfolds. You know, he's been the key theoretical you know, contact on these projects. Some of this work was also done in Shijie Wang's beamline at SLAC, where they've got a new ultrafast electron diffraction beamline, which, you know, works spectacularly well using mega electron volt electrons, whereas, you know, in our lab-based systems we're doing kilo electron volt ultrafast electron diffraction. There's some small quantitative differences between the two techniques, but, you know, by and large, in these kinds of experiments, you know, the lab-based results and the, you know, SLAC-based results are not super different. Okay, so you know, a few years ago now, when we used to attend March meetings, a few years ago, I went to a talk by Tony Leggett at the 2018 March meeting, which I found to be very interesting and quite profound. And he outlined the history of condensed matter physics and laid it out in sort of this diagram that I have here. Particularly, he concentrated on sort of the, you know, paradigm shifts that occurred in condensed matter physics. These may not have been as big as the paradigm shifts, you know, from, say, classical mechanics to quantum mechanics, but in our field, you know, he outlined a few paradigm shifts, and, you know, those were the ones that are highlighted in certain colors over here. You know, he had various reasons for assigning these to be the paradigm shifts in quantum mechanics, and I urge you to read his paper, which is very accessible. In particular, you know, he focused on the BCS theory of superconductivity, Fermi liquid theory, the renormalization group, and the fractional quantum Hall effect. Okay, those are the four that he sort of outlined here. But if we just take a step back for a moment and look at all of the things that were listed on this timeline, you'll notice that all of these leaps forward in our knowledge, and, you know, all these discoveries really have one thing largely in common, and those are that, you know, these ordered phases and, you know, theories all pertain to matter in equilibrium, right? And so for this part of the project, we actually, you know, for this, in reference to that, you know, history of condensed matter, which took about 100 years, and the kinds of projects that we're going to be talking about, you know, we wanted to ask, you know, the last 100 years have given us some really beautiful physics and continue to give us beautiful physics in near equilibrium physics. But are there, you know, things that we can learn about matter and different phases of matter that might exist away from thermal equilibrium, right? And so that's our main motivation for going away from thermal equilibrium, right? And there's some interesting cases out there. One could look at your coffee cup in the morning. When you pour milk into it, it's much more interesting. You have all these kind of interesting pattern formations in your coffee cup in the morning before it actually comes to equilibrium, when all the when the milk mixes in with the coffee, right? And so we can ask the question, why has condensed matter sort of concentrated on sort of near equilibrium physics for such a long time? And one possible answer would be that all inherently interesting phenomena in sort of hard condensed matter occurs in thermal equilibrium, or perhaps we've yet to put in as much effort to study hard condensed matter away from thermal equilibrium, right? It's just been a very difficult to access regime, right? And I'm hoping that it's the second, but to be honest, I can't say that I'm sure just yet. But hopefully, through this talk, I'll hopefully give you some indications that maybe number two might be true. So since I'm going to be talking mostly about phase transitions triggered with light, I think it's worth just reviewing quickly the kinds of phase transitions we have in thermal equilibrium, right? And you'll be familiar with at least these two classes. There are of course more, but these two classes of kind of equilibrium transitions, which are continuous and discontinuous. And on the left column over here, I've plotted, say, the free energy as a function of some order parameter, right? And you can see that the order parameter in this continuous kind of phase transition will turn on continuously at the transition temperature. Whereas in a discontinuous phase transition, the order parameter will suddenly click on at some transition temperature, and there can be some region of hysteresis in this kind of curve, right? The important thing to note about this kind of curve over here is that you can have several sort of metastable minima in this kind of free energy diagram, right? And so, when we're looking at exciting materials with light, one of the questions that we're going to be asking, and I'll put this, more formally on a future slide, but one of the questions that we can ask is, can we use light to actually excite materials from their ground state into a local minimum state, which may not be necessarily thermodynamically accessible, right? Can we access, these out of equilibrium states of matter and get them trapped in some way, right? And I'll talk more about that as we go on. But, I think one of the motivations for studying phase transitions in general is just because of how successful they have been in sort of capturing some semblance of universality, right? And so, I think the classic example exhibiting universality is sort of the specific heat as a function, well, not necessarily specific heat, but, various experimental observables will diverge at a critical point, right? Or exhibit some sort of scaling at a critical point. And, for instance, in this particular case that I'm showing here, this critical exponent alpha, which refers to the critical exponent for the specific heat, is identical for, say, the liquid gas phase transition at the critical point and the 3D Ising model, right? And that is quite a remarkable fact, considering that microscopically these systems have almost nothing to do with each other, right? And I think most of you know where this comes from, and it comes from the fact that at the transition temperature, we lose some sort of semblance of length scale. So the correlation length, which refers to how the fluctuations are correlated in the material, diverge at the critical point, and we sort of lose any semblance of length scale in the problem besides the system size, right? So if we just take a look real quick at what happens at this high temperature. So at this high temperature, you can see that there are fluctuations on some characteristic length scale way above the transition temperature. Way below the transition temperature, you would also see some sort of characteristic length scale. And so these fluctuations would be sort of the normal state fluctuations within the ordered state, right? Whereas at the transition temperature, the fluctuations, you don't see any semblance of length scale, and the fluctuations sort of, exhibit this sort of universality because all the microscopics are sort of hidden behind this fluctuation length scale, okay? So because this picture is so beautiful, we start to ask the question, how would this general picture change away from thermal equilibrium, right? And there is actually already this question has already been asked in the past, right? And that was asked within the context of what is now referred to as Kibble-Zurich theory, right? And in these kinds of experiments, the kinds of experiments that Tom Kibble and Wojciech Zurek imagined in the 1980s, well, Tom Kibble imagined it happening in sort of on a cosmic scale, but Wojciech Zurek, what he said was, look, we can actually try to do these kinds of experiments in the lab, and what we need to do is to quench the system from some high temperature state, right? So from some disordered state, which is depicted here in this paramagnet, right? And if we rapidly quench through the critical point, what will happen is, the fluctuations won't have time to become correlated over the entire length scale of the solid or the entire length scale of the system. And basically what will happen is you'll get some ordered puddles over here, some ordered puddles over there. And when they join up, there's going to be some sort of defect between these domains, right? And what was actually interesting about the theory, the Kibble-Zurek theory, was that they actually did predict some universality associated with these phase transitions. So if the cooling rate is much faster than some characteristic equilibration time, right? So note that it takes very long for the system to equilibrate near the transition temperature because of what is referred to as critical slowing down, but essentially it's because the length scales get so large in the problem. If you rapidly quench the system, you can actually get out some critical exponents in the defect density, right? And the defect density will be related to the correlation length in this problem, right? So the correlation length will scale, say, with the quench rate in this problem. And if you know your quench rate, which you control in the lab, you might be able to figure out the correlation length and the defect density, right? And there should be some scaling associated with this. Okay, so this was one example where if we went beyond equilibrium, you may be able to exhibit, there may exhibit some semblance of universality. Okay. So in the last few years, with the advent of ultrafast lasers and the like, there's been a new class of non-equilibrium phase transitions that we've been able to engineer in the lab. And these are photo-induced phase transitions, and the ones that I'm going to be concentrating on in this talk, right? And these are essentially phase transitions where, an electronic system, usually will undergo some sort of phase transition. So a gap will form, say, at the Fermi surface due to, the formation of superconductivity or charge density wave behavior or some other phase of matter. And what you do then with a light pulse is to excite these electrons near the Fermi surface up to some higher energy state, right? And because those were the very electrons responsible for the formation of the low temperature state in the first place, and those electrons then are excited, they have no, you can melt the order that was formerly there just by exciting these electrons. Note that this process is extremely non-thermal, right? This is not that we're turning up the temperature or something like that. This is, I'm exciting my electrons to some scattering states at some high energy, and the system then has no reason then to save that energy to form the superconducting charge density wave or low temperature state, right? Okay, and so with these phase transitions, we start to ask some pretty basic, we can ask some pretty basic questions here. And I'm not going to go through all of these, but the ones that we're going to try to, attack in our talk essentially is, how does the basic picture change, from our knowledge of equilibrium phase transitions when we start to excite these systems with light, right? Are there still fluctuations of the sort that we see in equilibrium, right? Is there some semblance of, criticality, or is there some universality associated with these phase transitions? And specifically for our talk, and the questions that I'm going to be really focusing in, because those first two were very general, the two that we're going to be focusing in on our talk are, can light be used to visualize sort of, when we excite a ordered system with light, can we use it to visualize a competing state of matter? And to what extent are there classes of materials with thermodynamically accessible metastable minima that we can try to access with light, right? And so I'm going to be talking about two examples in this talk, right? One material that exhibits a second order phase transition or a continuous phase transition, and one that exhibits a discontinuous phase transition. We're going to try to attack questions 3 and 4 within that context. Okay. So we have to choose a model system to study, and for these particular studies, I should say, we're going to study charge density wave materials, and you'll see why that why we chose these materials in a few slides. But essentially, a charge density wave material is one that undergoes a phase transition at some characteristic temperature. And basically what happens is the lattice and the electronic density become periodically modulated in space. Okay, and what happens is that when this periodic modulation occurs, you pick up a peak in your diffraction pattern that shows up below some characteristic temperature. So in this plot over here, I have taken some data on on a prototypical charge density wave material, titanium diselenide. And in this material, what you can see in the diffraction pattern is as you cool below the transition temperature, you suddenly pick up a Bragg peak or a satellite peak of the charge density wave, right? And the important thing to note about this peak essentially is that it is resolution limited, right? Meaning it's long range ordered, right? Over the length scale of as far as we can see in this material, right? So that's in this particular experiment, it's more than a micron, right? So it's long range ordered over a large scale in the solid. And as you reduce the temperature, the intensity of this peak grows, right? And you can see it has some sort of turn on that looks like a second order phase transition, right? And the important thing to note is that, as you reduce the temperature, what's happening to make these peaks, this peak grow more and more intense is that the atomic lattice is getting further and further displaced from its high temperature position, right? So it's forming this extra Fourier component at a greater and greater degree, okay? Now, that's not the only thing you can see using a scattering probe, right? In addition to seeing the long range order, you can also see fluctuations, right? And so, if we do an experiment where we do not just elastic scattering, as I showed on the previous slide, but you allow all the scattered X-rays to be detected by the detector, including all the inelastically scattered X-rays, what you pick up are fluctuations of the system as well. So you'll be measuring this quantity S of Q, which is the structure factor, right? But this is an integral over all frequencies, right? And if you integrate over all these frequencies, what you start to see is that there are these fluctuations forming as you approach the critical temperature, right? That start to peak up in the as a function of Q, and that's occurring because essentially you have critical fluctuations in the system, right? And so the thing I really want you to take away from this slide is actually in this inset over here, right? And so in this inset, what you can see is this broad peak underneath this long range ordered peak, okay? So you see the fluctuations are peaking up near the transition temperature and the long range order forms below the transition temperature. So just to remind you, so the long range order looks like this, right? Scales as the order parameter, whereas the diffuse scattering, right? The fluctuations peak up near the transition temperature and then will decrease once you go below the transition temperature. And this thermal diffuse scattering is really, its origin, at least in a charge density wave system, is arising from the fact that there's a phonon associated with this transition that is softening as a function of temperature. So at TC, this phonon will hit essentially zero frequency, right? Which is giving rise to this thermal diffuse scattering, okay? So, all right, so with that, rather long preamble, let's now turn to sort of our non-equilibrium experiments, okay? And so to do these kinds of experiments where we track, say the order parameter or the fluctuations as a function of time, we need to know about the characteristic timescales in our solid, right? And so for a phonon, if we're talking about a 10 millieV phonon, we're talking about a 400 femtosecond timescale, roughly, right? Versus electronic timescales, which are on the order of, if we took the plasma frequency, a typical plasma frequency in the ballpark of 10 eV, our characteristic timescales are in the ballpark of around 400 attoseconds, right? Which is very fast, right? So today, our typical ultrafast lasers, spit out pulses with a pulse width of around 100 femtoseconds or less. And so these phonon timescales are very accessible, right? But these electronic timescales are a little bit out of reach with our techniques. And so just to give you an idea of how these experiments are carried out, basically, there's a very nice analogy that can be made with these very beautiful images taken by Doc Edgerton in the 1930s and the 1960s and onwards, right? And so what Doc Edgerton did in these images to capture this kind of beautiful image over here, what he did was, he applied a very sort of ingenious trick, right? Because the shutter speeds, this picture was taken in 1957, right? And shutter speeds on most cameras, even today, are in the millisecond range, right? And so in a millisecond, if you were actually to take a camera shot in the millisecond range, this image over here would look like a complete blur, right? So how was he able to capture this crisp sort of microsecond image, even though his camera was working in the millisecond shutter speed regime, right? So what he did was he turned off the lights in his room, right? He had a little drop a droplet into a pool of milk that was sitting underneath that droplet. And he timed it just that when the droplet fell into that pool of milk, he had a brief microsecond flash, and he used the flash lamp to do that, right? But even though the camera is on for the whole millisecond or few millisecond shot, that flash is only on for microseconds, and that's how he's able to capture this crisp image, right? And so then what he can do is he can electronically time when that droplet falls from the dropper, and by delaying that time, he can actually capture several different images coming from different droplets and sort of patch together a movie, right? And that's essentially what we do in our experiments, right? When we do our experiments, we're not making a movie in the truest sense of the word, right? But we're patching together several different images and sort of making a movie that way when we do these non-equilibrium experiments. But they are very much inspired by this technique that Doc Edgerton, pioneered in the 1930s, right? So now we're gonna sort of dive into the experiments a little bit, okay? And basically, the material that we are going to study, at least for this part of the talk, is a rare earth tritelluride charge density wave system, okay? These are systems that have undergone a renaissance in the last few years, particularly through the group of Ian Fisher at Stanford. He's been growing these, and they've turned out to be really beautiful model systems for various reasons, and hopefully I can give you an idea of why. But basically, these systems have two tellurium sheets in this sort of almost tetragonal structure, right? And these tellurium sheets here, which are almost square, right, have a slight anisotropy between the A and C axes, which are the in-plane axes for group theoretical reasons. It's not A and B. But essentially, the seat of the CDW are these tellurium sheets, okay? There's a blocking layer, which is this lanthanum tellurium blocking layer over here, but that blocking layer doesn't really contribute to the Fermi surface, okay? The Fermi surface is really formed by these tellurium sheets over here. And what you'll note is that, we specifically studied lanthanum tritelluride, but you can substitute in any lanthanoid over here. Here you've got cerium, here you've got erbium, and essentially the Fermi surface stays essentially equivalent, right? All that atom serves to do is to apply chemical pressure to these compounds, right? Depending on the radius of the lanthanoid that you've chosen, okay? The important thing to note in this slide is that the A-axis and C-axis lattice parameters are almost equivalent, but not quite, right? And this small anisotropy between these two axes tip the charge density wave to form along the C star axis instead of the A. So even though there's only a very, very slight anisotropy, the dominant order is along the C axis, okay? Now, as I mentioned on the previous slide, there's a whole slew of these compounds, right? And you can substitute in almost any lanthanoid, right? And we chose to study lanthanum tritelluride because it's essentially the simplest compound of the lot. And by simplest, I mean, it has the greatest anisotropy between the dominant and subdominant orders, right? And so in our sample, only the dominant order forms, and it forms at around 750 Kelvin, way above room temperature. That's 750 Kelvin. Take it with a grain of salt because no one's actually ever measured the true transition temperature. But as you go to heavier and heavier rare earth elements, what starts to happen is that the transition temperature decreases of that dominant order, and some subdominant order. Some of these compounds also exhibit the subdominant order in thermal equilibrium. Okay. So in the subdominant order, when the subdominant order forms, you basically have two perpendicular charge density waves along the A and C axes, whereas in the dominant case, you only have a CDW along the C axis. Okay. So what's actually really interesting about these compounds is even in thermal equilibrium, so you can actually see the phase competition in these compounds if you were to perform an inelastic X-ray scattering experiment. Okay, and this is data taken by the Argonne group, actually from the group where I used to work. And what they did in this experiment was to cool this compound dysprosium tritelluride below the dominant order TC. Okay, and when they do that, what they essentially see is something very similar to what I showed you a few slides ago, which is that the phonon softens as a function of temperature as you reduce the temperature. This is the phonon relevant to the charge density wave. So the phonon starts to soften, it goes almost all the way to zero frequency, right? But what's interesting is that the phonon along the subdominant channel also starts to soften, okay? But once the dominant order forms, the subdominant order gives up and says, all right, I lost that battle and I'm gonna go back to where I was before. So you can actually visualize the phase competition in equilibrium reasonably well in dysprosium tritelluride, okay? So now for our experiments, as we're throwing the system out of equilibrium, we're going to be using this technique called ultrafast electron diffraction, right? And essentially what this is very similar to Doc Edgerton's picture of the milk drops. What we do in these experiments is we take a material, we excite it with a light pulse, right? And that excitation is analogous to his drop, right? And then we take an electron pulse and basically transmit it through the crystal. And that electron pulse is essentially our flash lamp, right? That's what allows us to capture that picture. So the electron pulses need to be very, very short temporally, right? As does the excitation pulse, the laser pulse. And so we then, make movies in this way, very similar to the way Doc Edgerton took his high-speed images. So this is what a typical electron diffraction pattern looks like for this material, lanthanum tritelluride, right? And you can see a few things. One is that you'll see these extremely intense Bragg peaks from the crystallographic structure. And you also see between these Bragg peaks, there are some weak structurally, because of a structure factor, some pretty weak Bragg peaks as well. Okay, so all of these three peaks are Bragg peaks. And flanking this sort of weak Bragg peak, you'll see another two peaks over here, which actually pertain to the charge density wave. Okay, and you'll see that in this particular compound, the charge density wave is incommensurate. So it doesn't have any underlying relationship to the crystallographic axes. Right? And so now what I'm going to do is I'm going to play for you a movie as a function of time and showing you what happens when we excite the material, right? And so this is, note that the order is already present at room temperature where we perform these experiments. And essentially when we hit this material with light, you can watch the dynamics of the CDW peak. So keep your eye on these two peaks or these two peaks in this movie. All right. So here we go. That's when a light pulse comes. You can see the charge density wave order melting, and you can sort of see the order recover as a function. Right. And I'll play that for you one more time so that you can look either at the trace or at the color plot, whichever one the opposite of what you looked at last time. Right. And so you can see order melts and it recovers on some characteristic timescale, which is on the order of picoseconds. Okay, so we can be a little bit more quantitative about this, right? We can plot the intensity of a CDW peak as a function of time, and we can plot the intensity of a Bragg peak as a function of time. And you'll see that the CDW melts on a very fast timescale, which was less than the resolution in this experiment, which takes about less than 1 picosecond. And in addition, it recovers on a timescale of around 2 to 3 picoseconds, right? So all of these processes are happening extremely fast. Right? One other thing I want you to note is that the Bragg peak actually intensifies as you melt the charge density wave. And that can be explained in sort of this cartoon picture where when I melt my charge density wave, I'm actually enhancing the Fourier component of my original lattice, right? And in a more sophisticated language, you can think of it in terms of this elastic scattering sum rule, right? The total elastic scattering has to be conserved. So when I melt my charge density wave, that scattering has to go somewhere. And on this extremely fast timescale, that intensity doesn't yet turn into inelastic scattering because the temperature has not equilibrated yet. So the temperature has not increased in my lattice. So all of that elastic scattering from the CDW peak has to go into the Bragg peak. Okay. So this is one of the kinds of things that you can observe in these kinds of experiments. But we actually saw something a little bit more interesting as well. So again, this is the diffraction pattern, this time using the mega electron volt system at SLAC. And what you can see here is, again, keep your eye on these two peaks, or say these two peaks, right? These, again, are the two CDW peaks flanking this sort of structurally weak Bragg peak, right? So keep your eye on these two peaks over here. And so this is the diffraction pattern before photo-excitation. And after photo-excitation, you'll see that you start to pick up two more peaks in the perpendicular channel, right? And as I mentioned to you previously, right, there's phase competition going on in these compounds. The anisotropy between the A and the C axes is very small, right? So we're actually picking up a signal of this sort of phase competition, right, in this out of equilibrium system. And this excitation is around, around 1 picosecond after excitation, right? And so if we were to take the difference plot of the intensity at 1 picosecond and subtract off what happened before the pulse arrived, you can actually see a couple things. One is that you see these peaks showed up, which I just showed you, right, in the perpendicular channel, the subdominant order channel. And the other thing you can see is that the dominant order starts to weaken significantly, right? That's indicated in blue. So red, the intensity went up, blue, the intensity went down, right? And this is 1 picosecond after the excitation. Now, you can also look at what happens, say, 20 picoseconds after, right? And by 20 picoseconds, actually, those two peaks are gone, right? They're no longer present. And what you end up with is essentially these streaks that you see in this sort of diamond shape around the central center point of this plot. And these are essentially the occupation of transverse acoustic phonons, which essentially is heat, right, in this system. That's where the heat gets dumped into. So after 20 picoseconds, the system becomes essentially thermally equilibrated. And that subdominant order is, no longer visible. Okay, and so let's just now play for you the full movie, right? So we can look at the dominant order over here, and as a function of time, you'll see that the subdominant order picks up and decays away. Okay, so here we go. So there we go. It starts to weaken. The subdominant order shows up. It disappears in sort of this kind of ghostly way, and then this dominant order starts to take over again, right? And so, we can be a little bit more quantitative about this, just like we were in the previous slides. And we can plot the intensity of this subdominant order as a function of time, and the dominant order as a function of time as well. And you'll see that the dominant order, the intensity decreases rapidly, right, after we hit it with light, and it recovers, whereas the intensity of the subdominant order increases and then decreases with some characteristic function of time. And you'll notice that these two timescales for recovery are very similar. It's almost as if they are competing as a function of time, right, rather than just in thermal equilibrium as a function of temperature. Right? And you can ask, okay, this may be some accident, right? But what we can then do is excite this material with several different intensities of our incident light pulse, right? And you can see that no matter what intensity we use, the characteristic equilibration timescales are always always identical for the dominant order to recover back to some semblance of order and the subdominant order to decay, right? You may note that these intensities at long times are not recovering back to their equilibrium values, and that's a good observation. And the reason that that's occurring is because we also have additional diffuse scattering arising from just heat being dumped into the system, right? So if I take you back to the previous slide, the thermal diffuse scattering, which we can capture, say, over here in this green circle, right, which is not related to the subdominant order or the dominant order, right? We just have an extra signal in the background over there, right? That's just thermal diffuse scattering, just from increasing the temperature, right? And so over here, you'll also see that it doesn't decay all the way back to its original intensity because we've got some extra intensity in these green circles, which also comes, which sort of is everywhere in Q space.
Okay, can I just ask a quick question?
Yeah.
So you're just plotting the intensities. I was wondering if you were able to also look at things like the widths of the peaks.
That is a very, very good question. And so basically, the answer is yes, of course we can, right? The question is, does the width give us any meaningful information? And it actually does, but the trouble with looking at the peak width, say along the dominant axis, right, is that we have both the long range ordered peak and we have that plateau underneath coming from the fluctuations. And for us in these experiments where our Q resolution is very poor, it's very hard to disentangle the two, right? And so that's a great question, because we're currently writing a paper specifically about this, because the A-axis peak, the subdominant order peak, actually allows us to just look at the fluctuations, because that's not long range order, right? So from looking at the A-axis peak, we can actually extract the fluctuation contribution and sort of separate out the long range order. And so that's an upcoming paper, but there I would say the peak widths are very hard to analyze in these experiments because of the poor momentum resolution. So this is getting back to sort of what I was just talking about, right? Which is that I showed this slide earlier where you were seeing that these two CDWs, the dominant order over here and the subdominant order, were competing as a function of temperature, right? And the intensity increases due to the fluctuations, right? And so that's essentially what we're seeing in this sort of out of equilibrium context. When the subdominant order is picking up, you can see that the intensity is increasing at that particular wave vector, right? But essentially it's losing out as the system equilibrates to the dominant order over here, right? So we're seeing fluctuations of the subdominant order show up after we excite it with light, is what I'm trying to get at. And so you can ask the totally reasonable question of, why would you ever do this when you can just warm your system up, right? And I think that there's a couple reasons that this is interesting. One is that the lattice temperature never exceeds 350 K in our experiment, right? If we calculate just the using the specific heat and measuring how many photons are incident on my material, our lattice temperature never exceeds 350 K. And I told you earlier that our TC was around 750 K, right? So we're accessing some really high temperature, quote unquote, high temperature regime without ever heating up our sample, right? At least the lattice subsystem, right? And the other thing I think that's more important here is the following thought experiment, right? Which is, if that charge density wave formed at a temperature higher than the crystal growth temperature, right? This phase competition would not be visible in thermal equilibrium, because once, if we go back to this slide, once the system, once the dominant order wins, the subdominant order essentially gives up, right? So if the dominant order formed higher than the crystal growth temperature, you would never know that in fact there was a subdominant order unless you performed an experiment like this, right? And you would be able to then access sort of that critical point above, in some sort of non-equilibrium way that would be totally inaccessible in thermal equilibrium, right? And I think that thought experiment really drives home the difference between this kind of experiment, right, and the experiment that you would perform in thermal equilibrium, right? You can potentially access the critical point that doesn't exist on the phase diagram. Okay, does anybody have any questions about this particular part of the talk? I'm about to move on to sort of my second part, so it would be a good time, I think, to chime in if you have any questions.
What was the laser wavelength again? I forgot.
Okay, good. Actually, I never mentioned, so good question. So we used 2 laser wavelengths in these experiments, and it didn't really make a difference to our results. One was at 800 nanometers, and the other one was at 1030 nanometers, and it exhibited exactly the same kind of phenomenon.
Is that expected?
Is what expected?
The independence on the wavelength?
Well, I would say for a system like this, it wouldn't be completely unexpected, because essentially what you're doing is you're exciting the electrons to some sort of higher energy scattering state, and as long as that process is occurring, it will be relatively wavelength independent. However, were you to excite at a very, very long wavelength, so that you were sort of accessing, say, the phonons, you were sort of resonantly exciting some phonons or something like that, then you might expect some qualitatively different results. Yeah. Okay, good question. All right. So if no further questions, I'm going to move on to sort of the second part of my talk, where we now explore, not a system that exhibits a second order, equilibrium phase transition, but a first order one, right? And in this part of the talk, what we're looking for is actually something a little different, right? We're trying to go from something that was, some very, very fast kind of transient behavior to trying to get something that lasts a little longer, right? Something that we can maybe control in a metastable fashion, right? And to do so, we're going to look at this other charge density wave compound, tantalum disulfide, which exhibits, a series of phase transitions, which are discontinuous, right? So tantalum disulfide exhibits two discontinuous phase transitions in its phase diagram, one at 350 Kelvin above room temperature, and one at around, in the ballpark of 200 Kelvin, right? And the important thing about the phase transition at the one that occurs, above room temperature is the fact that this charge density wave actually breaks mirror symmetry when it undergoes this transition. And this transition, it breaks mirror symmetry in the following way, right? This charge density wave is one that forms with these, Star of David kind of hexagrams, right? Of 13 atom clusters that form these little stars. And these stars can be tiled in two ways, which we call the alpha and beta configuration. Okay, and basically in these experiments, these alpha and beta configurations are related to each other by a mirror operation across this horizontal line over here, right? So were I to flip the beta to the alpha, I would need to mirror across this line. Okay? And that's the important thing about the phase transition that forms at around 350K. And this is a first order phase transition here that breaks mirror symmetry. And the reason that we were interested in this particular compound is because the timescale for recovery is just totally different compared to lanthanum tritelluride. As I showed you on the previous slides, lanthanum tritelluride recovers within a few picoseconds to its, quasi-equilibrium state, right? Whereas this compound, when you excite the system, it takes a really, really, really long time for the system to recover, right? So we thought, okay, if the system has a really long equilibration time, maybe there's some nearby metastable minimum somewhere that we might be able to access. So let's take a look. Let's take a look first at just the kinds of experiments that we can perform on this sample. Basically, if we just shine a very gentle pulse on the sample, what you'll see is not, some drastic change to the sample, but essentially you'll see oscillations of the charge density wave amplitude mode, right? And again, as I showed you in a previous slide where we had that elastic scattering sum rule, right? Where, the Bragg peak intensified when we melted the CDW peak. Here, we're not melting the CDW peak fully. We're just sort of hitting it slightly. And what it's doing is its amplitude mode is oscillating as a function of time, right? And what you can see is that, the Bragg peak then oscillates with that same frequency as a function of time, but out of phase with the superlattice peak, so that there's this transfer back and forth of spectral weight between the Bragg peak and the superlattice peak, right? So the CDW is weakening, the Bragg peak is intensifying, and it happens in an oscillatory fashion. Now, this is just kind of cool thing that you can see using ultrafast electron diffraction, but let's dive into the physics a little bit more here, right? And I'll come back to why I showed that amplitude mode in a bit.
Sorry, can I ask one quick thing to clarify? So this is it's a transmission experiment?
It's a transmission experiment, that's correct.
So yeah. The samples must be pretty thin then?
They're around 50 nanometers, yeah.
Okay, so 50 nanometers. So because in tantalum disulfide, I know certainly the stacking along, they're probably thin along the c-axis, so the stacking along that axis is quite important.
Yes. Yes, it is.
Okay, so I just wanted to orient myself in terms of it's still basically a bulk sample, but
it's still a bulk sample. That's correct. It's still a bulk sample, and it's preparing these samples is pretty challenging, right? But as I'll show you in the coming slides, the mirror, this thing breaks mirror symmetry, right? So as you go through this mirror symmetric transition, every single layer has the same mirror symmetry, right? And I'll show you that more closely in just a couple slides. But essentially, as I mentioned previously, you have the choice of tiling in this alpha configuration or this beta configuration. And so you will see long range order in these samples using in one sort of mirror orientation, right? And so in this case here, I've drawn A, and you'll see that the whole sample exhibits this sort of alpha orientation, right? And the way that we know that is by doing diffraction, right? And so this is a diffraction pattern of tantalum disulfide at room temperature, right? Or sorry, higher than room temperature, above the incommensurate to nearly commensurate transition. So this is around 370 Kelvin, right? And what I want you to keep your eyes on at this point, I'm again going to play you a movie, but this movie is going to be as a function of temperature, not as a function of time. What I want you to do is just to keep your eyes on this peak and this peak over here. Those correspond to two charge density wave peaks, right? And as I reduce the transition temperature, mirror symmetry is going to be broken, and those peaks will sort of exhibit that broken mirror symmetry, right? So here we go. You can see that those peaks rotate as a function of temperature, right? So as I reduce my temperature to below the transition temperature, they rotate away from that blue line, right? I'll play that for you one more time just in case you missed it. But essentially, it's making the choice to go into the alpha configuration and not the beta, right? And there's long range order in alpha, right? And basically what we then did was we said, okay, at room temperature, it's already made its choice. It already chose the alpha configuration. Let's now shine a laser pulse on the sample, right? And what then happens is that not only do you see 6 peaks around the Bragg peak, right? You actually now see 12, right? So if you reduce the temperature of the sample further, you can see these 12 peaks much better than you did before, right? And what I want to drive home here is that these peaks, once you establish these peaks, these are stable. So all I've done is to shine a single laser pulse on the sample, and now this thing is metastable, right? This new diffraction pattern does not change as a function of time anymore, okay? And what you can furthermore do is shine another laser pulse on this sort of 12 peak configuration, and it'll go back to its 6. So far, we have not been able to reversibly, and controllably do this, right? This is still probabilistic, so we need like 2 or 3 pulses to get this to sort of switch and then switch back, but it can be done, right? We're going to continuously work on, trying to get this to be stable and controllable in some way, right? But essentially, it's just 1 femtosecond pulse gets it to go into this 12 peak configuration and back to the 6 peak configuration. And so you can ask, why are there 12 peaks? And from what I've said previously, it's probably reasonably obvious, but what we can do is we can go do sort of micro diffraction. So since this is stable, what we did was we took our sample to a TEM, right? We did diffraction in these little circles, which is around like a 1 micron spot, right? And you can see that, in certain parts of the sample, you actually get a beta domain, and in some parts of the sample, you get an alpha domain, right? And this comes back to Kemp's question, which is, how thick are these samples? These samples are 50 nanometers thick, and so these domains are going through the entire crystal, right? Through the entire crystal, it's all in one mirror, right? It's not that there's there's one orientation in one layer and one orientation in another layer. It's that it's spatially separated, right? And along these yellow regions, we weren't able to tell the difference between the alpha and beta configurations. There were just 12 peaks in those places. So since the resolution here was a little coarse, we wanted to collaborate with a TEM group that had expertise in sort of atomic resolution TEM, and I'll show you those results in a second. But one of the things that we can do now with the amplitude mode is to actually use the amplitude mode frequency to actually get at least get a qualitative feeling for the size of the domains, right? And we noted that when the domains were relatively large, the shift in the amplitude mode frequency was relatively small. So this gray line right here denotes the amplitude mode frequency of the pristine sample, right? And so if the domains are relatively large, the amplitude mode doesn't change in frequency very much. But if their domains are small, and if we use a really intense laser pulse and the domains are small, the amplitude mode frequency shifts quite a bit. Okay, and this is something that we can characterize reasonably well, right? Okay, so that tells you one thing. So let's move on to our TEM results, which I think are actually really cool, right? So again, this was done in the group of Lina Kurtkuris at Cornell. And so her graduate student, Ismail El-Bagari, who's now a Roland Fellow at Harvard, performed these TEM experiments. and where they actually took sort of atomic resolution TEM images. So these are the tantalum atoms, right? And what they then do is to Fourier transform this image to get a diffraction pattern out. Okay, and what you then see is that these peaks are split in the characteristic way, due to the domains, right? So there's not just the clockwise peaks or the counterclockwise peaks or the alpha peaks or the beta peaks, they're both, right? And what they then did was to Fourier filter, looking at just a set of these two peaks over here, to Fourier filter those images back into real space. And this process led us to the following conclusion, right? Which is that you can see the CDW. If you just filter those peaks, you can see the CDW really well in these lines, right? But you'll note that these two red lines, which are parallel, in this case, this one lies perfectly along the CDW direction, and in this case, it's cutting across, right? So what's happening is that there's a domain over here, which is alpha, and a domain over here, which is beta. And the separation between these two domains is actually a bunch of dislocation type topological defects, okay? And you'll see these topological defects look something like this as in the inset over here, right? And they were actually able to basically go along a whole slew of these defects, and they look something like this as in a cartoon. So this, looking at this image hurts your eyes a little bit. So this one over here sort of shows you how these domain walls kind of form at these, at these angles, right? So since the angular difference between the alpha domain and the beta domain are not that great, you can actually see this whole, you can see this connection between the two domains that form at these topological defects. Okay, what was actually really cool was when they took a full-blown map of these topological defects along a domain wall, right, along a very large region of the domain wall. You can see that the topological defects actually form a lattice structure, right? They're spaced around 4.4 nanometers apart, which actually corresponds to a 13 tantalum atoms, right? So the 13 tantalum atoms, if you were to draw what's happening, it's that this part has one mirror, this part has another mirror, and if you count this distance from here to here, that's perfectly 13 tantalum atoms. And so the domain wall is sort of forming some pattern that looks like this. And so that's somehow, when we've excited our material with light with a single laser pulse, the domain wall forms in this kind of, really kind of unique way, right? Which has been seen in crystals previously. It's called a low angle grain boundary, but it's never been seen in a CDW texture prior to our experiment. Okay. And so they can even, do these kinds of maps where they actually see the two domains, where this blue region corresponds to, say, alpha, and this red region corresponds to beta. And they can do this as a function of temperature as well. And what's actually kind of interesting is that, while the alpha and beta are very well separated in the nearly commensurate state, as you cool the sample down into that, past that secondary phase transition, the regions start to get really messed up. But if you warm it back up, they then resegregate into separate patches once again. Okay, this isn't super important, but I just thought it was cool. Anyway, I've been talking long enough, so let me just summarize what we've learned real quick, which is, there's a bunch of questions, related to light-induced sort of phase transitions. I hope that I've just been able to give you a little bit of a flavor. We looked at one sort of second-order transition material, one first-order transition material, and you can see the behavior is totally different, right? One, the recovery is very fast. One where the recovery is very slow, right? But it nonetheless, I think we've been able to address in some capacity some of the questions I posed at the beginning of the talk, which is, how does the basic picture change in going from equilibrium to non-equilibrium? And I hope I've been able to give you a flavor for how the picture changes slightly. But the cool thing is that I think we were actually able to visualize these competing states of matter out of equilibrium. And in addition, we've shown that we can sort of access, some sort of metastable structures, be there due to topological defects or some other kind of reason, that we're actually able to do these kinds of things in these experiments that are really hard to do in thermodynamic equilibrium, right? We need these light pulses to really, the advantage, one of the advantages of light pulses is just that they're so fast, so that when you quench, these defects can sort of don't have time to equilibrate and sort of disappear, right? So anyway, with that, I hope I've been able to convince you that, this is a worthwhile pursuit. And not only that we can actually do some pretty cool things with this, right? In the first experiment, there are some fluctuations that we can see which may not be easily accessible in thermodynamic equilibrium. In the second case, we're sort of engineering these topological defects with light, right? And we've only chosen CDW systems to study here. There's tons of other materials out there. So the landscape is, I think, pretty large for these kinds of experiments to be explored in the future. With that, I just want to thank you one more time, and I'm happy to take any questions.
All right, lots of clap emojis. So it's open for questions if anybody has any.
I have a question.
Yeah, sure.
Okay, this is very interesting. May I assume that the electron gas after the excitation and the atomic lattice are completely decoupled in terms of temperature?
That's a great question, and I think I think in most of the literature, in a lot of the theoretical literature, there's this sort of 2-temperature model or 3-temperature model where they treat the electrons and lattice as some kind of 2 decoupled systems. In this kind of system, it gets a little bit complicated because the charge density wave is a highly electron-phonon coupled beast, right? So to be honest, I'm not 100% sure whether or not, I suspect that it's not theoretically feasible to make that decoupling in this particular scenario.
Okay, so in equilibrium statistical mechanics, we have all the basic concepts, the tools that we can resort to, right? Things like equipartition, things like detailed balance, things like a entropy argument. And here, if we throw all these tools away, how should we think about this?
That's a great question, and it's an ongoing battle that we have to face, right? And so one of the reasons I brought up this sort of elastic sum rule in my talk is because we have to resort to things like, sum rules apply more broadly than just in equilibrium, and so that's one of the kinds of things that we can lean on, right? Whereas, as you said, we got to throw away detailed balance, but at least, some rules give us some sort of constraint, right? And I think, for most of our studies, at least from a theoretical standpoint for now, that's mostly what we are leaning on, right? That's our sort of general, and hopefully we can build on that structure a little bit more, but, it's tough. It's tough. Like you said, our footing starts to slip out from under us a little bit.
Mm-hmm.
Thank you.
So,
apologies.
Go ahead.
Yeah, sorry, I have a question. In atomic systems, there have been interesting results from coupling electromagnetic light with the atoms themselves. So electrically induced transparency, for example, is one really interesting property. Are there any sort of analogous predicted states of the coupled system, light plus matter?
Yeah, definitely. So, a few years ago, I think probably the most outstanding result in this direction was the exhibition of Floquet block states on the surface of a topological insulator. You might be familiar with that result. I'm not sure, but
yeah. So Vesna, one of our colleagues, has been deeply engaged in that field.
Yeah, so that's one result where I think that there's a strong analogy to be made with atomic systems, right? It's essentially our light-dressed state, right? Which is essentially very much in this mold, right? Of doing electromagnetically induced transparency and Rabi oscillations and this kind of thing, right? And so the other place where people have sort of seen this kind of behavior is when looking at excitons. And using excitons, what you can do is you can essentially create a light dress state such that you can see effects like an optical Stark effect, where there's sort of level repulsion with the exciton and your light dress state, right? So yeah, people are starting to explore these kinds of results, and I would say at the moment those Floquet states and this sort of optical Stark effect, they are very much analogous to the atomic systems. But I think the most interesting result in the last couple of years in this direction has been from Germany, where they actually showed that by creating these Floquet states, you can actually drive a topological phase transition into an anomalous Hall effect, right? That I think from a condensed matter standpoint, that was really interesting because we're looking at not just engineering, say like light dress states. We're trying to drive new phases of matter, and so that one was particularly a standout result. Yeah.
Thank you. Very nice talk.
Thank you. Thank you.
So I'll just ask, I guess related to Sean's question. So you kind of set up the talk with a distinction between first and second order phase transitions, and then talked about that in terms of light-induced phase transitions. But I'm just kind of trying to get a sense of when it's a light-induced or out of equilibrium transition, what really distinguishes it being first from second order? In what sense can you even say, or did I get the language wrong and you really just meant systems that had thermal first and second order phase transitions?
I really meant systems that exhibited thermal, but I think the distinction between the two, when you go out of equilibrium, and this is right now just some intuition, it's not any sort of rigorous statement that I'm making here, and it probably is wrong in certain contexts, but the point I was trying to make is that in a second order phase transition, the recovery time tends to be a lot faster than in a first order phase transition, where you can get trapped in a metastable minimum for a little while, right? And so the recovery rate, since it's so much slower in a system when you have a first order phase transition, right? You can start to get all these like kind of weird metastable effects that occur, right? Because your system is trying to quench, it's sort of being quenched back into it's trying to go back to its equilibrium, but as it's getting trapped, you start to get some inhomogeneous structures in your system.
And in out of equilibrium, you could get into a metastable.
Yeah,
state,
I guess so. It's starting to get pretty meta.
Yeah.
Yeah.
Okay, I'll let it hang for a second if anybody has questions. Okay, I guess no other questions. Thanks a lot. That was a really, really great talk.
Thanks. Thanks for the invitation. I was really, really happy to do this, and yeah, really, really happy to get to meet a few of you.
Yeah, hopefully sometime you can visit.
Yeah, that would be great. Yeah. All right. Well, thank you.
Yeah. See you.
See you.